hopefully you're hearing some sound. So did you hear the sound okay?
I could hear fine.
Okay, so what you just heard was an example of change ringing. So throughout the years, bells of various shapes and sizes have often been used to announce important events. Bells have been around for millennia, and there's archaeological evidence of bells in Asia dating back around 5,000 years. So here I'm ringing a bell in Korea that's old, but not quite that old. For our purposes, though, of looking at change ringing with its connections to mathematics, the roots lie in 10th century England, where any Saxon possessing 500 acres, a church, and a bell tower was able to become titled, being granted the title of Thane. So as a result, there are more than 5,000 bell towers for change ringing in England today. In comparison, there are less than 300 change ringing bell towers across the rest of the world. So originally the bells were struck or a rope was pulled, making the clapper or bell swing, and the clapper's going to strike the bell multiple times, usually with no control. However, after the 14th century, improvements in how the bells were hung gave ringers more control with the ability to make a bell ring just one time, exactly once, which then led to the birth of change ringing around 1610. The picture on the left is a bell at rest in the Old North Church in Boston, which may make you think of Paul Revere. In fact, Paul Revere was a change ringer, which gave him access to the Old North Church bell tower, connected with his famous midnight ride on April 18th, 1775, and the instructions, 1 if by land, 2 if by sea. Interestingly, this silversmith later became a bell maker. So at first, wooden bells were used to practice change ringing so as not to disturb the neighbors for miles around with the sounds of the big tower bells like you heard at the beginning of the presentation. And then in 1660, the first tuned bronze handbells were created, allowing bells to be played not only for change ringing, but also for melodies. But what is change ringing? So in change ringing, the tower bells are rung in permutations, which are shufflings or rearrangements. Change ringing takes a team effort with each person responsible for one bell. And we'll take a look at a little video here. So suppose our bell tower has N bells. We're going to label them from the highest pitched bell 1, called the treble, to the lowest pitched bell labeled N, called the tenor. So in change ringing, the bells are rung one at a time at a constant beat. A change is ringing each of the N bells once in some permutation. So for example, with 6 bells, there would be 6 choices for what bell rings first, and 5 choices for what bell rings second, 4 choices for third, 3 choices for fourth, 2 choices for fifth, and then 1 bell left to ring last. So for 6 bells, there'd be 6 times 5 times 4 times 3 times 2 times 1, called 6 factorial, or 720 permutations. So change ringers are ringing what's called a sequence of changes. If all n factorial permutations are rung, then it is called an extent, while a peal is a sequence of at least 5,000 changes. So here is a table based on the number of bells. And so we see the number of changes required for an extent and an estimate of the time it would take a polished change ringing team to play that extent. So with 4 bells, there would be 24 changes or permutations, which can be played in about a minute. While with 8 bells, there are over 40,000 permutations, and it would take about a day to play them all. So you can probably guess the number of times a full extent has been played on 12 bells, since it would take about 38 years to play. Interestingly, the English mathematician John Wallis, in his treatise of algebra published in 1685, about 75 years after the birth of change ringing, uses change ringing as an example when he discusses permutations, which he calls alternations. He mentions the number of changes for 5, 6, 7, and 8 bells. Then Wallace discusses if changes were played on 24 bells, it could not have been dispatched from the beginning of the world to this day. And he shows his calculation for figuring out how much time that would have taken. He also displays a table showing the number of changes based on the number of bells. If you look on the right column, it looks like Wallace is using an X to denote factorial. The exclamation point that we use today to denote factorial was first used by the French mathematician Christian Cramp in 1808, about 120 years after Wallace's algebra. So a change ringing composition must meet 5 conditions. The first one is it begins and ends with what's called rounds, where that's playing the bells in order from the highest to the lowest. Then no other change should be repeated. So, for example, if you had 5,000 changes, how are you going to make sure there are no repeats? So that was an issue that those who wrote change ringing compositions had to address, which led to some interesting connections to mathematics that we're going to discuss in a bit. The third condition, from one change to the next, a bell can move at most one position. This condition is actually due to the physical constraint of the bells. It takes 2 to 3 seconds for a bell to ring and then swing up ready to ring again. So a bell can't physically ring last in one change and then ring first in the next. Then fourth, no bell placed in the same place for more than 2 changes. I put this condition in gray because there were times even from the beginning when this was relaxed and a bell might play in the same position for up to 4 changes. And then last, each bell sounds exactly once per row or change. So let's start by looking at changes on 3 bells using these conditions. So we have to start with rounds. So ringing the bells from the high bell to the low. Then in the next row or change, where could the first bell ring? Well, looks like it could ring first. So we'll come back to this possibility. Can it ring second? If you look at it for a while, that looks okay so far. Can it ring last? Well, no, this would have 1 moving 2 positions, which violates condition 3. So we have 2 possibilities where the treble bell can ring in the second permutation, either first or second. So let's assume it's going to ring second. Then where can the number 2 bell ring? Can it ring last? Well, this would make 3 move 2 positions, so that can't happen. So the number 2 bell is going to have to ring first, forcing the 3 bell last. So if you continue going through, making sure you're meeting all the conditions, there are no more choices. And we get all 6 permutations of the 3 bells. And then we end with rounds. So I'm going to play this for you. The bells are in order 1, 2, 3 from left to right. So this is what it would sound like on handbells. So if you recall, we had the possibility with the treble bell playing first in the second change, and considering this one, possibility there's no other choices for it either. And it actually is the same sequence of permutations or changes, just in the reverse order. So there's only these 2 ways to ring changes on 3 bells. So this is an example, what's called a plain hunt in change ringing. So it starts with the 1 bell hunting up and over the 2 bell, and then up and over the 3 bell. Once on the edge, it rests their 1 change before it hunts down over the 2 bell, and then the 3 bell, and rests their 1 change. So changes on 3 bells, then the 2 is hunting down and then up, and the 3 bell is hunting up and then down like the 1 bell did. So let's move to 4 bells. So if we do a plain hunt on 4 bells, hunt with the 1 up and down, with the 2 down and then up, the 3 up and down, and the 4 down and then up, we end up with rounds. And if you count the number of permutations there, we only have 8. So we're ending with rounds, but too soon. So we only have 8 permutations of the 4 bells, when actually there should be 24, 4 times 3 times 2 times 1. And if we do this in general, starting with rounds, heading up and down with odd numbered bells and down and then up with even numbered bells, we begin with rounds after 2n permutations instead of n factorial. So get rounds too soon. So there are 3 operations then in change ringing: hunting, dodging, and placemaking. So let's take a quick look at permutations and groups before talking more about change ringing. So one way to write permutations is a 2-row notation. So if I have the change, I'm going to ring 2, 4, 3, 1. Writing this as a permutation using 2-row notation, since the first bell is playing in the 4th position, under the 1, I'm going to put a 4. And then second bell rang first, so I put a 1 under the 2. Third bell rang third, and the 4th bell rang second. And we just saw the definition of a group in the last talk. So a non-empty set together with a binary operation. So in our case, we've got our permutations, and we're going to compose them, do one permutation followed by another. So that is closed. We do get another permutation. It satisfies associativity. So if we have 3 of them, we can group in either way. We have an identity permutation of doing absolutely nothing. And we have an inverse permutation of to swap everything back to where it started from. So the set of all permutations of n objects, S sub n, forms a group with respect to the operation of permutation composition. Another example of a group that we're going to see in a second, use it, is the symmetries of the square. So the dihedral group, D4. So we've got the identity of do nothing to the square, and it's still there. If I reflect the square across this vertical side bisector, if I didn't have the numbers there, I wouldn't be able to tell that I had reflected it. So that's a symmetry. And the permutation 1 and 2 swapped, and 3 and 4 swapped. I can rotate the square 90 degrees and write that as a permutation. I can reflect across this diagonal, so the 2 and 3 would stay fixed and the 1 and 4 would swap. I can rotate 180 degrees. I can reflect across this horizontal side bisector, so 1 and 3 swap and 2 and 4 swap. Rotate 270 and then reflect across this other diagonal, where 1 and 4 staying fixed and the 2 and 3 are swapping. So I get 8 permutations. This forms what's called a subgroup of the group of all permutations. So a subgroup is a group inside a group using the same operation. Now, if you have a subgroup, you can form what are called cosets. So a left coset of a subgroup H is take some fixed element A and combine it with everything in H, where the A stays on the left. And it turns out the family of all cosets, as A ranges over all of G, forms a partition of the group G. So back to our change ringing, looking at what's usually the first composition people learn. So it's called plain bond minimus. It starts with a hunt, plain hunt. If I hunt one more time, it'd be back to rounds. So we use what's called a dodge. So we keep the first 2 bells the same, swap the second 2. Hunt again. I hunt one more time, I'd get a repeat of the top change in that column. So I dodge again, keep the first two the same and swap. And then hunt. If I hunt one more time, I get a repeat of that third column's first element. But if I do a dodge, I'll get rounds. So if we were doing this in person, at this point, I'd ask for volunteers, but can't really do that virtually. So you're stuck with listening to me play it. So we have all 4 factorial or 24 permutations of these 4 bells. And if we look at the top row and write them out, we've got the identity permutation, another permutation that when we square it gives us the last entry in that third row. And if we multiply it by itself again, we get back to the identity. So we actually have a subgroup of the group of all permutations as 4. Now, if we look at the next row, we have this permutation, which if I take it times the, in the first row, the second element, we get the second element in the second row. And take it, the original one times the top of the third row, we get the next permutation in that second row. So we are getting a coset, AH, where A is the first permutation in that row. And in fact, if we do look at the second row, we get another left coset, the third row. And so each row actually forms a different left coset. And then if we look at the first column, that's actually that group D4. And then the columns form the right cosets of D4. So the change ringers actually knew some of this structure. So Fabian Stedman was one of the first to investigate change ringing compositions, and he was a contemporary of Newton. So it's not until about 100 years later in 1770 when we have Lagrange investigating permutations, trying to generalize known methods for solving cubic and quartic equations, trying to find a solution for the quintic because he didn't know that it didn't exist yet. But he made some important discoveries for group theory while he was doing this and analyzing the solution of quartic equations. That involved the 24 permutations of the sum of pairwise products of the roots of the original equation. So the top row is actually a subgroup of S4, and each row is a left coset. So very much like looking at plain Bob minimus, but at the columns. The modern version of Lagrange's theorem states that if you have a group with n elements and H a subgroup with m elements, m divides n. And the idea of the proof is making a rectangular array where the top row is the elements of H and each subsequent row is a distinct coset. And once you prove that's a partition, then you have that the number of elements of G is the number of rows times the number of elements in the subgroup H. So the early proofs of Lagrange's theorem use this rectangular array of cosets, just like change ringing. Here's just a quick clip from Jordan's article from 1861, where he proves the general case of Lagrange's theorem. And it is exactly what people like Fabian Stedman were doing to come up with change ringing compositions like plain Bob minimus. And if you compare these dates, we see Fabian Stedman was using cosets and change ringing about 100 years before Lagrange and 200 years before Jordan. So it looks like maybe the mathematicians should have spent some time in belfries with the bats, and they might have come up with group theory much earlier. So I hope you've enjoyed this introductory look at connections between mathematics and change reading. There's so much more that I don't have time to talk about, but I hope it spurred your interest to learn about other connections. Math is really all around us, and we really do live in a small world. So thank you.
Thank you, Cynthia.